Thank you. So, first of all, welcome to my talk. This is what we're going to run through today. We're going to look at the problem of scaling financial transactions. Then I'm going to introduce TigerBeetle and TigerBeetlex, which is the Elixir client for TigerBeetle I wrote. And then we are going to pick a little bit under the hood and maybe show some future ideas for it. A little bit of intro on myself. I'm Riccardo Binetti. You can find me online as Arbino usually. I'm a senior backend developer at Remote, and I've been fortunate enough to be using Elixir as my main language since 2017. So let's start with a terminology question. What is a transaction? As software developer, we usually think as transaction as database transactions. But in this talk, we're going to talk about financial transactions. But the two things are very related. And in fact, the Postgres tutorial shows a database transaction implementing a financial transaction. So your application begins the transaction. Then you have to read from the database. You have to read the balance of Alice and Bob. And notice that you have to lock the database row for them. Otherwise, you can incur in loss updates. So you're locking the whole row to do the financial transaction. Then your application performs some side checks. So for example, ensuring that the balance is enough. And you can implement some of those in the database. But if they're dynamic, you usually do it on the application side. And then you write back stuff. So you update the balance, and you possibly insert also the transfer, because you want to have like a trace of what happened and why. And then you commit the transaction. Notice that to implement a single financial transaction, we have a single database transaction, but we are actually using 6 database queries. And in fact, in real-world system, the average number of SQL queries for a financial transaction is between 10 and 20 queries. So you have a factor of 10 multiplication between financial transaction and SQL queries. You might say, OK, let's just shard the workload horizontally. So we put some of the accounts there, some of the accounts there, and we can distribute the work. The problem with that is that transactions are not distributed equally, but they have a Pareto distribution usually. What happens is a single transaction touches 2 accounts, and usually the top 20% of accounts are touched by 80% of transactions, which means that this lock is very costly because it's locking 80% of your transactions. On top of that, we actually live in an increasingly transactional world. So we have lots of online transactions, physical transactions. There are real-time payment systems implemented like UPI in India, which processed 12 billion transactions in January 2024 alone, PIX in Brazil. And then there is also things that is not directly related to money, but it actually increases the number of transactions, like renewable energy. Now that the energy price depends from the sun, you don't want to transact your energy once at the beginning of the day. You want to do it throughout the day, and this multiplies the number of transactions by 1000x factor. So how do we scale financial transactions? This is what TigerBeetle was designed to do. So TigerBeetle is a reliable, fast, and highly available database for financial accounting. And it was designed from the ground up to be a database dedicated to financial transactions. So it implements lots of clever tricks to have a really extreme performance. But the main trick that TigerBeetle uses is that it speaks the language of financial transactions. So instead of having the previous 10 SQL queries, in TigerBeetle, one financial transaction is represented by 128 bytes with 0 serialization and deserialization. So it's just 128 bytes of binary data that goes onto the wire. Now, if one transaction is so small, then why don't we batch a bunch of them? So we are amortizing the network cost, we are amortizing the I/O cost, and we're going to see that we are amortizing also the consensus cost because TigerBeetle is distributed. So one TigerBeetle query is actually composed of 8,000 transactions that all stay in a single megabyte exchange on the network and stored in the storage. How is it possible to do so? This is the struct, the zig struct that represent a transaction, and it's called transfer. And do we have everything we need that we had before when we were using queries? Let's look at this. So we have an ID that represents univocally a transfer, a transaction. Then we know we have to transfer some amount from somewhere to somewhere. So we have debit account ID and credit account ID. We have the actual amount, and notice that the amount is always positive. We're going to see why when we look at accounts. And then we have the timestamp, so we are able to identify when the transaction happened. So we have all the W questions, and the last question, like the what, the why, and the how, is represented with application-specific code. So if you look like ledger, for example, is just a number, and you can use ledger to logically isolate accounts and transaction between different logical domains. So an account in a certain ledger can only transact with another account in a same ledger. You can use that for parts of your application. You can use that for currencies, for example. You can use that for whatever you want. And code represents an application-specific code that tells you the reason why this transaction was done. And then you have user data, 3 user data fields with our 128, 64, and 32 bytes that you can use freely to connect the data from TigerBeetle to your application database. And let's look at the account too. And there is the ID here too, so each account has its own ID, of course. And that's what I was mentioning before, as you don't get an explicit balance into the account, so everything is positive. The amount transferred in the transaction is positive, and the direction is given by who is the creditor and who is the debitor. Here still, when some debits are posted to an account, then you increment debits posted. When some credits are transferred to an account, you increment credits posted. So to calculate the balance, you basically do credits minus debits, or debits minus credits, but this is an accounting thread that we don't want to go into today. But the TigerBeetle documentation explains this for you. And we still have these 3 user data fields. So like before, we were able to store also the fact that a certain account was for Alice or some other type of metadata. What TigerBeetle tells you is that you should use TigerBeetle as your data plane, so to store only data strictly related to transactions, and store all the other metadata inside your generic database. So for example, in Postgres. So this decouples the 2 sides and lets you have extreme performance on the transaction processing, while you have data that changes slower, like the name of the person holding the account that can be processed normally in Postgres. Now, performance is one of TigerBeetle's goal, but the other one, since we are dealing with financial data, is safety and durability. So I mentioned already before that TigerBeetle is actually a replicated database, and it uses view-stamped replication, which is a less known replication algorithm, but it was actually developed by Brian Oakey and Barbara Liskov in 1988, 1 year before Paxos. And view-stamp replication basically implements a replicated state machine. So all TigerBeetle replicas actually execute the same state machine code, and the consensus mechanism ensures that they receive the same inputs in the same order. So everything in TigerBeetle is strictly serializable, the highest serializability level. And this ensures that all replicas have the same state and the same output, because they are state machine with a deterministic input that produce the same state and output. And the cost of consensus, I was mentioned before, is amortized by batching. So we batch 8,000 transactions. It means that we wait for consensus both for writes and for reads, but we're amortizing that for 8,000 transactions. So it scales very well. And the nice thing is that TigerBeetle integrates consensus and replication with storage fault tolerance. What this means is that, again, like deterministic, like all TigerBeetle replicas have the same data file bit by bit on disk, which means that if one replica detects that its storage is faulty, it's able to ask for just the faulty block to other replicas and not to do a full repair like usual replicated database do. Like, you don't have to transfer the whole data file, you just have to transfer the corrupted block, which makes things automatic. You don't have to do full repair like in Sheila or Cassandra. And on top of this, like, these are all mechanisms, but someone has to write software, and usually that's the most valuable place to look at. So TigerBeetle uses Tiger style, which is a set of rules that is partially derived from the NASA's Power of 10 rules, which basically, I won't explain them all here, but they are rules to ensure that your software behaves well, and you write software ensuring that everything goes well. Like, for example, putting lots of assertions at the beginning and the end of the function. And one interesting quote that I extracted from there is that about assertions is assertions downgrade catastrophic correctness bug into liveness bugs. The only correct way to handle corrupt code is to crash, which sounds strikingly similar to to the let it crash mantra in the Beam world. So they don't want corrupt state, they prefer to crash. Okay, but how we detect those crashes? Like, Postgres has been around since like 20 years, 30 years. How do we compete with that with a database that has been born in 2020? All the determinism I talked about until now is very useful because TigerBeetle does automated deterministic simulation testing. So you're able to simulate a whole TigerBeetle cluster by simulating I/O, network, storage, and time. So you're actually able to make time travel faster. And basically 100 simulation cores that keep running in the TigerBeetle CI are able to simulate 2 centuries every day. So now TigerBeetle has the advantage on Postgres. And the nice thing is that if TigerBeetle, if the developer, which is the name of the simulator, finds a crash, everything is deterministic. It's just going to open an issue with the seed, and you can just take the seed, plug it into your local copy, and you're going to get the exact same crash. And you're able to debug it and fix it, hopefully. So I talked about all these nice things about TigerBeetle, the database, which is written in Zig. So what does it have to do with Elixir? You can actually use TigerBeetle in Elixir using TigerBeetlex, which is the Elixir client for TigerBeetle I wrote. It's a NIF written in Zig, which is implemented on top of the Zig TigerBeetle client. So this is how all TigerBeetle, high-level TigerBeetle clients are implemented. They use the Zig TigerBeetle client and just implement bindings on top of it, which ensures that all of them use the same state machine for the client, because the client also is an active part in the replication mechanism. TigerBeetle basically gives you a message-based API to talk with TigerBeetle, a blocking API, and automatic mapping between TigerBeetle binary data and Elixir structs. So let's look at the available requests. And in fact, since TigerBeetle is it's not a general purpose database, it actually exposes a very limited set of operations. So the only right operation that you're able to perform in TigerBeetle are create accounts, that creates an account, and create transfer, which creates a batch of transfer and a batch of accounts. Then, after you do that, you're able to read requests, to do read requests that look up the accounts and the transfers by their IDs, and these are batch 2. So you pass a batch of IDs, and you get back a batch of accounts or transfers. And there is also some read requests that use a filter, so they use secondary indexes. This is actually, for now, an experimental API, but they're already exposed to the clients. The first two basically allow you to get all the transfers regarding a specific account. And the second one, you get all the balances, which are the different balances in a certain point in time. So you have the whole history of how the balance changed for an account. And the second two, basically, you're able to retrieve some accounts or some transfers using filters on ledger, on code, on the user data, basically on metadata. You're able to query all the secondary fields of the structs. Let's look at how you use, actually, TigerBeetlex from Elixir. Let's start from the message-based API. So you create a client basically just by passing a cluster ID, which is a uniquely 128-bit identifier of the TigerBeetle cluster, and you pass all the addresses of all the replicas. And you create the client. And notice that here, the client variable can and should be shared with all the callers of the API, because the underlying Zig client, on top of your manual batching on the application side, the underlying Zig client also does automatic batching while it's waiting to send out a request. So you're able to have potentially also another layer of batching if you're not able to fully employ the batches on your application side. And then to send a request, it's rather easy, like to create accounts. Accounts are just Elixir structs. You instantiate the two, you create the two structs, and you pass a list of accounts, and the list there is the batch, so they can be up to 8,189. And you call client.createAccounts, and you can get a reference back. What you can do with that reference is call receiving the code, which is basically a shorthand for a receive block. So you can also spell it out if you have more things you're waiting on for a receive. Or if you're already inside the gen server, you can just handle this in an handle info block. And you decode the response, and you get a list of an OK tuple with a list of responses. The blocking API is strikingly similar, but it's just blocking. So you start a TigerBeetlex connection, which is actually a partition supervisor, and you pass a name explicitly, and that name will be what you use to perform the same request. So everything is basically similar. Instead of getting the reference back, you directly get the response back. When should you use one versus the other? So the message-based API can plug into an existing gen server architecture, and it provides more async, more flexible async handling. We're going to see why in a little bit. But the client needs to be passed to the process. Like, you can't instantiate a new client every time. You have to keep the client somewhere and pass it to all the processes. So with the blocking API, it's easier to get started with, because the client itself is centralized, because it's held as state inside the processes, but it could leave the caller blocked. Let's quickly see some advanced usage. So these are very basic, like I just show you how to create some accounts, but TigerBeetle is able to implement lots of stuff on top of this basic mechanism. First of all, let's look at error responses. So when you create the account as before, you're actually, if everything goes well, you're just going to receive an empty list. So OK, empty list. This is because TigerBeetle which another small optimization, assumes that everything goes well and just sends results for things that didn't go well. So in this case, the second account has an ID of 0, which is not allowed. And so the result will be a single entry saying that the account with index 1 in the batch has an error, and the error is ID must not be 0. Notice that the first account, account 0, still got created. So it's not like if we send a batch, then everything is atomic. But if you want that, you can use linked events. So linked events allow you to have different atomic chains of events inside your batch. So they work by, this work by setting the flags field of the account or transfer. It works the same on both. With the account flags struct with the linked field as true. And basically, to construct a linked chain, you have to pass true, 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 and false to the last one, and all the ones that have true as linked and plus the first that has false will form a link chain. So here we are creating 3 accounts with linked true, true, false. This is a 3 events chain. And what happens is that if we try to do the same and the second one still has ID 0, we are going to get 3 errors now because everything is atomic, so either the whole chain succeeds or the whole chain fails. And the second error is still ID must not be 0, and all other events get the linked event failed error. Another advanced thing you can do with transfer is two-phase transfers, which get their name from two-phase commits in distributed transactions. So basically, you can do transfers in 2 different phases. The first one is the reserve funds phase, where you basically set the transfer flags to pending true. And you can determine a timeout if you want. So in this case, if you recall previously in the account struct, there was the posted credits, but also the pending credits. This is going to increment the pending credits. And this, in the second phase, so the funds are now reserved, so they count towards the like the ability of not going under 0, for example. And in the second phase, you can either post the pending transfer, so you basically confirm it, and the funds are actually removed from the account by passing the post-pending transfer through and the pending ID for the previous transfer. And notice that you still have to pass the amount because you can't post the transfer with a lower amount, for example. So you can reserve 100 and then you post it for 50. Like when you do gas at the gas station, you do this. Or you can void the funds. So basically the whole thing gets thrown away and the pending funds get back to the account. Or you can expire it. So if you pass a timeout, which is not mandatory, the pending transfers will automatically expire after 30 seconds. For more advanced usage, the TigerBeetle documentation has a whole section on recipes, which are really cool. Like, for example, they show practical example of how to implement a currency exchange in terms of transfers, multi-debit, multi-credit transfers, balance conditional transfers. And the cool thing is everything is implemented in terms of transfers. Like for balance conditional transfers, which are transfers where you want to check, for example, succeed only if after the transfer the account has at least $100. You don't have to read the balance, check on the application side, and do the transfer. You can do it using only transfers atomically using some control accounts where you do pending transfer. Basically, everything is transfer foo. Now, this is nice and well. There are some caveats which are intrinsic to how TigerBeetle is built. And first of all, the TigerBeetle documentation actually tells you that I show you that I put the ID on the Elixir side, but actually the web application or like the top caller should generate the ID and pass it and thread it through the whole application. This is because TigerBeetle uses the ID as an idempotency key. So this guarantees that if your request fails, but actually maybe it succeeded on the TigerBeetle side, but your application got disconnected and the client doesn't know that, if you send the same request with the same ID, TigerBeetle is going to reply exists. So I know you already sent that, I already saw that, you're okay. But it also, like, it doesn't assume that since it has the same ID, it's the same stuff. It checks all the fields, so it's also going to reply exists with different amount. So you know that you actually successfully did the transfer and you're trying to send the same one but with a different amount. So on the other side, so you're generating the ID on the top side, the timestamps are created by the TigerBeetle server. This is not particularly strange because like you usually generate timestamps on the database side, but the particular thing is that here is that no two events have the same timestamp. So accounts and transfer always have different timestamps because everything is strictly serializable and the timestamp basically gives you the strict order of everything that happened on the TigerBeetle, inside TigerBeetle. And the third one, which connects back to why the message-based API is nice, is that by default, TigerBeetle requests are retried forever. TigerBeetle never times out. It keeps retrying the request and it doesn't surface network errors to the caller. This, again, is done to try to ensure consistency as much as possible. But if you use a blocking API, this could mean that the caller keeps being blocked by the TigerBeetle call. But we are cool because we have messages. So if you use message passing, then your gen server is not going to receive the message. Never mind, you're just going on. You're just able to go on with your life. So let's have a quick look under the hood on how this thing is implemented. So this is what happens when a message-based API caller calls the TigerBeetlex client. So it calls the TigerBeetlex client function, which calls nif.doctor, which calls the zignif, which calls tbclient.submit, which is the Zig's client function. And notice that there is no connection here because the Zig TigerBeetle client handles as his own asynchronous execution mechanism. So what this means is that you submit and the caller returns. So the NIF execution is extremely quick. And then the on-completion callback gets called when the response is received. And the NIF is actually sending a message to the message-based API caller. So this is cool because when I approached NIFs the first time, I thought about them like these blocks of synchronous code that had to execute really fast because otherwise the scheduler would scream at you. But actually what we can do is that from any place in the code, if we have a PID in hand, so not just in the place that gets called from the Elixir side, but any C code that has a pillar, a PID in its hand, is able to like send a message to the Elixir side of things, which is cool because if your C application already has its own async execution mechanism, you're able to just use message passing to send the message back to the Elixir side. And this is how the blocking API is implemented. Basically, this is where we were before. These are a bunch of receiver, which are just gen server, which are going to call the client and receive the message we were talking about earlier. And the blocking caller will call one of the receivers via a partition supervisor, which will also be a registry, and just wait for the gen server reply. There are a couple of nice things that are made possible by Zig in this NIF. So first of all allocations on the NIF side show up in Erlang.memory. This is not strictly allowed by Zig, because basically if you in C you can just call alloc beam and get up some memory allocated by the beam and the distract from this. But the cool thing about Zig is that every function that allocates in Zig accepts a custom allocator as first parameter, which makes it really easy to use the beam allocator everywhere. In standard library function, in third-party library function, having a standardized interface where you can pass the allocator around makes it really easy. And the other cool thing is that all the bindings or the Elixir structs representing the TigerBeetle data are actually generated using Zig comp time. Zig comp time is a mechanism of executing Zig code at compile time that allows you to basically introspect inside Zig types and obtain typed information which is not available at runtime. What this means concretely is that we have this account struct that we saw before, that is basically a bunch of fields with their type. And from the Zig code, we are able to call type info on the struct and iterate through all the fields and have some information like what is the field name, what is the field type. And you can call type info on field type too. So if the type is an integer, you're going to see, is it signed? How many bits does it have? And what does it mean? That you're able, from some Zig code, we emit the struct with also the type specs, and we also emit the binary pattern matching. So we just get the TigerBeetle binary data here, and with comp time reflection, we are able to generate the code to unpack that and transform it in an Elixir struct. And all of this basically is just a single command away. You execute Zig build bindings, and all the Elixir code in the bindings folder of TigerBeetlex gets generated from the upstream TigerBeetle code. So updating the TigerBeetle version is just a matter of bumping some version numbers. And last thing, like, do I have to have a Zig toolchain on my system to do that? No. This is a side project I implemented while working on TigerBeetlex. Basically, build.zig allows you to use the Zig build system to build your NIFs, which basically it's the equivalent of Elixir make, but instead of using a make file, you use a build.zig file. And the nice thing is that you don't need anything on your system. It's just going to download the Zig single binary, unpack it, and just build your NIF. And you can use it not only for Zig NIFs, but also for C NIFs. So, quick round of ideas for the futures. And this does not mean that I'm going to implement all of them, but it's just random ideas. So first of all, user-defined structs. So what I want to be able to do is, instead of having a generic TigerBeetlex.account, I want to be able to do something like that. So myapp.account and do use TigerBeetlex.account.schema, which could make it more nice to work with the user data, because then you're able to rename the user data field to account UID, for example, or map ledger and codes to explicit atoms, so your code is more readable. Then after that, so after this is implemented, possibly, one idea I had was to implement an hash data layer, which I think would be nice, because like the core idea about TigerBeetle is you have to use TigerBeetle for transaction and another database for your normal data. And the hash makes it super nice to join data from different data layer and I think it would be even nicer than all the official clients. And then CDC handling, so this is a currently open merge request. TigerBeetle started implementing change data capture, so you get a stream of events when anything changes in TigerBeetle, and this is actually, it uses RabbitMQ for event storage, and we have Broadway, so why not add that to consume CDC data inside the TigerBeetlex client. Maybe upstreaming as an official client. I don't know, it might be an idea. And that's it. Questions?
All right. Thank you, Riccardo. We've got time for about one question. So, how is balance handled with multiple and async operations running? Is it possible to get the balance in real time?
I think the balance in real time is solved by CDC, so you get all the events, and you can consume all the events from RabbitMQ, and I guess you can like update a live view, for example. But multiple async events, like a single TigerBeetle client, the Ziegler TigerBeetle client, always allows only one in-flight request. So it enqueues all the other ones that come after it, and this is still to guarantee strict serializability. So you can have multiple clients in your applications, but actually the TigerBeetle docs recommends using one and sharing it as much as possible.